Okay, so let's talk about finding the volume of revolution for an object on the Cartesian plane. So there's two different ways to do this. The first thing we're going to talk about is what's often called the disk method. Okay? The disk method is based on the volume of a cylinder. Okay? So if you've got a cylinder that looks like this, we've got a radius here, we've got a height here, and the volume is the area of the base times the height. Area of the base is going to be pi r squared, and the height will be h. So we're going to use this idea for the volume of the cylinder to find the volume of this object of revolution. So the idea is that we've got a function here, f of x, and we're going to take the space underneath it between two arbitrary points here along the x-axis, a and b. We're going to take this thing and we're going to rotate it around the x-axis. And so what we get from that, let's see if I can draw this here. Kind of like that. Okay, so something like that. And then the cross section here is going to be a disk. That's why we call this the disk method. And there's the thickness, which corresponds to the height of the cylinder. So the volume of this little cylinder right here, just this one cylinder, we've got a radius for it right here. Okay. That radius is actually going to be the y value, or f of x. The height here, which is important to the volume of the cylinder, the height here is delta x. Okay. So the volume of the cylinder is going to be pi r squared delta x. And then the idea here is that we're going to sum all of these up. We're going to take a sum. Well, we're going to take the limit as n goes to infinity. And we're going to take n of these little cylinders, right? We're going to calculate their volume, stack them all up, and then add them together. And so we'll call this pi r squared delta x. And then this was the foundation for the area under a curve. Okay, when we take this, the limit of this sum, that's what creates an integral. So this is the integral from a to b of pi r squared, and then we change that delta x into a dx. So this is the formula for the disk method. Now often the r will be equal to f of x. But in a lot of problems, you know, that are a little bit trickier, the r will be something a little bit different. It'll be something related to the f of x. Okay? All right. So there's the foundation idea for what's called the disk method. And this is the formula that we're going to be using to find the volume using the disk method. And this is on that formula page that's posted on the course website. Okay, so let's talk about something that's called the washer method. So this is a little bit more complicated. Let's see here. Let's erase some of this. We're going to keep some of it too, but let's see. Let's just erase the whole thing. And over here. So the washer method is based on a situation where you've got a cylinder with a hole cut out of the middle. So we've essentially got our same cylinder, except that this one has a hole all the way through it. Okay? And then the radius for the large section, we'll use a capital R. And then we've got the radius for that interior section, we'll use a lowercase r for that. And then we've still got the height. So the idea here is that the volume for this object is going to be the whole volume of the big cylinder, and then you subtract out the volume that's missing in the middle, which is a little cylinder. Okay? So the volume of the big cylinder is pi capital R squared h, and the volume of the small cylinder in the middle is pi lowercase r squared h. And so if we want the volume of the whole thing, that'll be pi capital R squared h minus pi lowercase r squared h. And so we can factor these out, pi h r squared minus r squared. Okay, so that's the fundamental idea. So we're going to go back now and look at, let's see here. What do we want to do for this? Well, let's take two functions. Okay, so we've got, let's say we've got an f of x here, and then we've got a g of x here. And the idea for this washer method is that when we rotate this around the x-axis, it's this area in between the curves that's going to get rotated. This is going to be open space down here. Okay, so let me color this in just to make that more clear. So that's the space that's going to get rotated around the x-axis and create our three-dimensional object. So this outer section will be right here, and then we'll have another line right here. And so this is where this washer comes from. You've got this interior section that's empty, that's the empty section in here, and then you've got an exterior piece, that's where our volume is out here. So this object, I mean, what does this thing look like if we were to draw it? Let's see, on top, you know, it would be something like this. It's got these curved sides, kind of like that. And then you've got this situation where most of the volume, or all of the volume really, is in here, okay? And then that big piece in the middle is empty. All right, so the idea here is that we've got this interior section right there, and there's our thickness, which is a delta x, and this one is the same way, also has a thickness here along the x-axis, which makes that delta x. Okay, and so this is the little r right there. I know this is getting a little bit messy. And then the big R is going to extend all the way to the edge. So if we take our formula and do the same thing that we did for the disk mesh method, then this is going to come out to be the integral from a to b of pi big R squared minus little r squared dx. Right? And that's coming again, that's coming from this limit as n goes to infinity, the sum I from 1 to n. And so let's see, this is going to be pi big R squared minus little r squared, and that h from our formula is this delta x right there, that thickness. Okay? And so this is our second formula that's on the formula page for the washer method. It's pi big R squared minus little r squared dx, and we integrate from a to b. Okay, so there's the derivation for these formulas. Now let's look at some examples and see how we apply these ideas. Okay, so first we'll look at a couple of disk method problems, and then we'll also talk about a couple of washer problems. All right, so let's see here. So the first example I want to look at is problem number 2 on this first handout. So let's write the problem down here. Let's see. So we've got function y equals 1 minus x squared, and the line y equals 0, and we want to rotate this around the x-axis. So let's see, let's do a little sketch of what we're working with here. Y equals 1 minus x squared, so this is an upside down parabola, and if you want to graph this on the graphing calculator, that is often helpful. And you've got intersections, or you've got roots here, -1 and +1. Okay. And then the y equals 0 just cuts this off right here. So here, I'll erase this in a sec, I think. But I just want to show you. So there's the area that we're dealing with, and that's going to get rotated around the x-axis. Okay? So it's important to identify the space, the two-dimensional space, that's going to get rotated before we get into this. Okay? So that's in here. And so then if we rotate it, we'll get a kind of corresponding mirror image down here. All right? And our cross-section is going to look something like this. There's the thickness along the x-axis. And when I do the next example, you'll see why I keep talking about this thickness. This is along the x-axis. We'll look at some that are along the y-axis. Okay? And our radius right here, there's our radius. And that's the function value in this case. That's just 1 minus x squared, f of x, or y, depending on how you want to think about it. Okay? So, this is all set up nicely. If we want to, we can think about what this thing is going to look like. It's going to look something like some kind of a, something like some kind of a Christmas ornament maybe, okay? Kind of like that, okay, in 3D. So, if we take that formula that we were talking about earlier, where the volume is the integral of pi r squared dx. So, let's see. Well, first we need to know the limits of integration. Well, in this one it's pretty straightforward, and that's why I was identifying those roots a minute ago, is because those are our limits of integration, -1 to +1. So, we want to integrate from -1 to +1, pi. Our radius is 1 minus x squared, and then dx. Oh, all squared. There we go. Okay. Now, we really can't integrate this the way that it is. We're going to need to square this out. All right? And that's a very important piece to doing this, is the algebra. All right? So, if we do 1 minus x squared times 1 minus x squared, that's going to be 1 minus 2x squared plus x to the 4th. So that's what we need to integrate. From -1 to +1, pi 1 minus 2x squared plus x to the 4th dx. So now let's do the integration. We'll have the pi there. This will be x 2/3 x cubed, x to the 5th over 5, and we're going from -1 up to +1. And so let's see here. We'll have pi 1 minus 2/3 plus a 5th, and then minus -1, that'll be positive 2/3, and then minus a 5th. And this negative sign will change all of these signs here. And again, you can do this on the calculator. You can evaluate this on the calculator if you want to. This is going to come out, and I'm going to do that in a minute. But in any event, this is going to be 2, and then minus 4/3, and then plus 2/5. Okay? So what is that going to be? Let's see. I'll check this on the calculator in just a sec. This looks like it's going to be 2/3 plus 2/5, which should be 16 pi over 15. So let's double check that. 2 minus 4/3 plus 2/5, 16 pi over 15. Good. Okay. So that's problem 2. That's a disk problem. It's getting rotated around the x-axis. All right. The next example we look at is going to be problem 6. That's going to be a disk problem, but that's going to be going around the y-axis. And so that's going to work a little bit differently, and we'll talk about that in just one sec. Let's see here. Okay, we'll leave the formula up there. In problem 6, let's see here. We want to take y equals ln x, y equals 1, y equals 2. So this is defining the area that's going to get rotated, and x equals 0. And then we want to rotate this around the y-axis. Okay. So again, first off, if you want to use your graphic calculator to see what this graph looks like, I think that's a good idea. It's really helpful to get a good sketch of what's happening. So the y equals ln x is going to look something like this. Okay. And then we're going to have y equals 1 and y equals 2 like that. Okay? And then this x equals 0 closes that off here. So again, like I was saying, identify the area that's going to get rotated. So here it is right here. I'll shade it in and then I'll erase that shading in a second. Okay? So that's the area that's going to get rotated, and we're going around the y-axis this time. Okay. So if we rotate this around the y-axis, we're going to get like a mirror image over here. It's going to look something like that. And our cross section is going to be right here. Notice there's no gap in the middle. That's why this is a disk problem and not a washer problem. And I'll talk more about that in a minute when we see some examples of washer problems. So here's the thickness of that cross section. This is why I keep talking about it. This is a delta y, right? That tells us that we're going to be integrating with respect to y. Okay? Our radius here is the x value. So if we take y equals ln x, we need to turn this around into a function of y in a similar way that we did some of those area problems in winter term. Okay? So if y is equal to ln x, right? This is a base e. That means that e to the y is equal to x. That is our radius. Okay? And because we're integrating with respect to y, our limits of integration are going to go from 1 up to 2. So now I think we're ready to build our integral. So we're going to integrate from 1 to 2 pi. Our radius is e to the y power. That's going to be squared. And put the differential in there. It reminds us what we're integrating with respect to. We're integrating with respect to the y variable in this case. The process is the same, but your limits of integration, it's important that those match the variable that you're integrating. So let's see. If we square this e to the y, and again, we've got more algebra popping up here that we need to be able to do. So now remember, with this e to the 2y power, if we want to integrate this, we need a 2 hanging around. You can make an explicit substitution if you do that. All right, we'll balance this with a 1/2. And so our integral here will be 1/2 pi e to the 2y from 1 to 2. So I'll put the 1/2 pi outside here, and that'll be e to the 4th. And then when I plug the 1 in, that'll be e squared. And so this is our answer. And we can approximate this. Let's see, I think I wrote that down earlier. About 74. So this comes out to be about 74.156 if we evaluate this and make an approximation. Okay, so it's the same concept when you're rotating around the y-axis, but it's important to identify that thickness is a delta y, so that and the real key here is to make sure that this is a function of y, to turn it around into the form x equals instead of y equals. Sometimes it'll be given in the form x equals, sometimes it won't. Okay, but if you're integrating with respect to, well, if you've got a thickness here that's a delta y, and you're rotating around the y-axis, you're going to need a function of y to identify the radius of the disk or washer, depending on what you're working on. Okay, so that's problem 6. That's a disk problem going around the y-axis. So next we're going to look at a couple of washer problems. One is a washer problem going around the x-axis, and then we'll see a washer problem going around the y-axis. So let's take a look at those. Okay, so now we need the washer formula, where the volume is the integral of pi, big R squared, minus little r squared, dx if we're going around the x-axis, it'll be dy if we're going around the y-axis. Okay, let's see. Which one do we want to do here? Problem 10 is a good washer problem that goes around the x-axis. And what do we have here? Y equals 1/4 x squared, and y equals 5 minus x squared, and we're going about the x-axis. Okay, so again, we want to get a good sketch of what this looks like. I encourage you to use the graphing calculator to help you visualize what this is going to look like. So let's see here. The y equals 1/4 x squared. It's going to be a parabola that's kind of stretched out. This 1/4 causes it to fall like that. And this will be y equals 1/4 x squared. And this 5 minus x squared, this is the classic upside down parabola that's been pushed up 5 places. Kind of looks like this. Okay. And we can find these intersection points. You can find them on the calculator if you want to. If you set these equal to each other, it comes out pretty easily. This is x equals -2. This is x equals +2. If you plug them in, you can see that this will be here y is equal to 1, and over here y is also equal to 1. So this is the point 2, 1, and this is the point -2, 1. Okay. So first off, let's identify the area that is going to get rotated. Okay, and again, I'll do that and then I'll erase it so it doesn't clutter up the diagram. So there's the area right there between those two curves. That's what's going to get rotated around the x-axis. So let's see if I can make a sketch of that. This is a little bit tricky. So what we want to do here is kind of make a mirror image of the picture above the x-axis. Okay. So there's that. Our cross section, I'll put right here. Here's the exterior cross section, and then we've got that interior cross section right there. Okay, these both have thicknesses that are along the x-axis. In each case, that thickness is a delta x. We've got a little r right in here. That little r is the parabola. That's 1/4 x squared. The big R is right here. And that's this is the other parabola, the 5 minus x squared. Okay, so that's the key to doing these problems, is identifying those R's. Okay, if you're doing a disk method, there's just going to be one of them. If we're doing the washer method, there's going to be 2 of them. And let's see, what does this thing look like? This thing has that little hole at the top, kind of goes to the side like this, right? And then has a hole at the bottom. Okay. So in 3D, that's kind of what this thing is doing. All right. Oh, and actually, if you look at this, it's not a perfect cylinder on the inside, right? It's doing this. Something like that. Okay, so now let's set up our integral for this. We've got our limits of integration. We're integrating with respect to x because our thickness is a dx, delta x along, it's a thickness along the x-axis. And so our limits of integration are going to go from -2 up to +2. Pi, the big R in this case is 5 minus x squared. Oops. All squared. And then the little r inside here, that's the 1/4 x squared. All squared. And we're integrating with respect to x. Now again, here's the algebra. We need to square these out. Okay? So, 5 minus x squared all squared. Let's see here. That's going to be 25 minus 10x squared plus x to the 4th. And then here, this is just a single term, so that's going to be minus 1/16 x to the 4th dx. So our integral here from -2 to +2, pi, 25 minus 10x squared, and then this is 1x to the 4th minus a 16th x to the 4th, so that's going to be 15/16 x to the 4th. Okay. And as I like to say, and we haven't done any calculus yet, right? This was all just algebra right here. So now we're set up to take the integral. So, let's see here. We're going to get pi 25x minus 10/3 x cubed. And then, let's see. So this is going to be x to the 5th over 5. The 5 cancels with the 15 and leaves us with 3/16 x to the 5th from -2 to +2. Okay, so let's see what we get here. Pi, that'll be 50, and then 80 over 3, plus 32 times 3, 96 over 16, so that'll be 6. And then minus -50, another 80 over 3, and then another 6. So this is going to come out pi times 100 minus 160 over 3 plus 12. So let's take the calculator out here, see what we get. 100 minus 160 over 3 plus 12. So this is 176 pi over 3. If you want to, you can call this, it's 58 2/3 times pi, and if you actually multiply that out, you can also express it as about 184.3. Okay, so any one of those three forms for the answer is fine. Okay. All right, so that's a washer problem going around the x-axis. All right. So let's look at one more on this worksheet. This is going to be a washer problem. This next one, which one are we looking at here? Problem 8 is a washer problem that goes around the y-axis. So let's see what that looks like. Okay, problem 8. We start with, now this is actually that same parabola, y equals 1/4 x squared, and then x equals 2, and y equals 0, and we want to go about the y-axis. So again, let's make a picture. Draw a sketch. So there's our parabola. Y equals 1/4 x squared. X equals 2 is out here. and then that y equals 0 closes it off. So again, here is the piece of area that is going to get rotated. Okay, I'll shade it in before I erase that so that we don't clutter up the drawing. So this thing is going to get rotated around the y-axis like this. Let's see, so if we want to draw a 3D version of this, let's see, something like this. Again, we want to get a mirror image over here, and then our cross-section will look like that. So let's fill this in. So if this thing is getting rotated, you know, in 3D, what this thing is going to look like is going to be a cylinder with straight sides, right? Except that in the middle of it, you're going to have this big gaping hole in the middle of it. All of the volume is going to be on the edges there, okay? And we'll notice actually something that's interesting about this when we finally make the calculation. Okay, so if we look at a cross-section of this, here's the washer, this is the interior piece, this is the exterior piece, okay? So along the interior, there's the thickness of that interior piece, and then here's the thickness for the exterior piece. And again, these thicknesses are along the y-axis, right? This is a delta y. So that's telling us we need a function of y here. This is a function of x, and so we're going to need to restate that. Before we get to that, let's identify the radii. Here's our little r right here. And then the big R extends to here, big R. So here's the thing, in this problem, notice that that big R doesn't change as you go up and down. It's a constant. It's always equal to 2. Okay, it's that distance right there. Now this distance right here does change, all right? And so, again, this is equal to the x value, and so we need to restate this function as a function of y. So we've got y equal to a 4th x squared, so 4y is x squared, and x is the square root of 4y. That's our little r, square root 4y. Okay, so now we've got everything set up here. We've identified the big R and the little r. Now we just need our formula. Oh, do we have our limits of integration? Well, down here on the bottom, we've got y equals 0. So that's going to be our lower limit for the integration. Up here, if x is 2, right, then this is going to be 1/4 of 4. So that's going to be the point 2, 1. So we're integrating from y equals 0 up to y equals 1. And then we want these functions of y in here. Now this one's not really a function because it's a constant. So it's 2 squared and then minus square root 4y all squared. Well, this works out really nicely because when you square a square root, the 4y just comes out. And so this is the integral from 0 to 1, pi 4 minus 4y dy. Okay, so now we can integrate. There's our pi, 4y minus 2y squared from 0 to 1. So pi times 4 minus 2, and then minus 0. So this is 2 pi. So that's our answer. One thing I want to mention about this, when I was drawing that diagram, if you take a cylinder and cut a parabolic shaped piece out of it, this is half the volume that gets cut out, and what's left is also half the volume. It's really pretty interesting, and you can parameterize this, and you can calculate this in general, and it holds true for any parabola, is that what's inside here is going to be half the volume, and what's left out here is also going to be half the volume. Okay? That's just sort of a peripheral idea, not really necessary to doing the problem. This is really all we're looking for on this one. Okay, so that's it for this first handout. I'll post a second handout that's got some more of these disc and washer problems. and I'll go over some of those as well. So we'll see you then.